हाँ चल तो रहा है.
Power again. And we're back at Google Map Meets as well. Sorry, guys. So
tomorrow we will collect gather here at 10. Then you will have your exam discussion, and after that you will have at 11:30 lecture in the science auditorium, and then we will get you certificates. So and after that we Torah and Bible. So this is the program for tomorrow. Please tolerate us for last.
okay, so yeah, thank you all for the patience. Happily the power is back on, and I hope it will stay like that to finish this lecture. So we were talking about particle separation and the reasons why we need to separate particles, which could be environmental. From memory, we got stuck at the circulating tumor cells, which were a little bit more bouncy than the other cells we've got around. In a bioreactor, we may want to culture yeast and separate the bacteria away from the yeast, which again means that a cell separation may be very useful to be having taken place in a continuous flow. In blood, separating the blood cells away from the plasma is very useful for chemical analysis, because we can then do the chemical analysis in a cell-free medium. Traditionally, particle separation can be done with a filter, membrane filter. So you just either have a cross flow or a tangential flow filter. You push the liquid through and the permeate is particle free. Another thing that you can do to separate particles is do centrifugation based on different densities. And the higher the density of the compounds, the deeper they will be sinking down into the centrifugation tube. Can even have a density gradient in your centrifugation tubes, which then do allow you to separate different cells based on their characteristic density. So if you've got different cell types, these cell types have different densities. You can use that for density centrifugation. To sort them a little bit more funky, there is flow cytometry, which is where you give a fluorescent label or a label with any other fingerprint if you're detecting with another matter to the cells. And typically you do that with an antibody. For example, for cancer cells, there's a lot of tumor-specific markers that sit on the outside of a cell. So you can raise an antibody specific to that marker, put a little light bulb on that antibody to say, hi, I'm here. So if you hit it with a laser, you get a fluorescent signal. And you know in the flow cytometer setup, the system then knows, the cell that's now there is fluorescent. Therefore, it's a tumor because it's got that tumor-specific marker on the sides. And it can then selectively sort these cells, either only count them or sort them into different outlets. For example, if you're working with circulating tumor cells, you can selectively collect the circulating tumor cells in a specific reservoir and then do further genetic screening on them to figure out if the patient's tumor may be sitting in their liver, in their kidney, lungs, or brain, or anywhere else. So once you've got the cells, you can do a lot more testing with them. And again, it's really good if you can do that on a liquid biopsy on only a blood sample. Then when you have to start investigating and take tissue biopsies, from all the different organs in a patient, because then your patient is full of all kind of perforation holes to take these biopsies. So microfluidic methods are very suitable to deal with particle separations because their dimensions are kind of similar to the cell's microorganisms. Microchannels we're talking about 500 micron. Small organelle clusters are getting up to 100, 150 micron. Your typical blood cell is around 20. Bacteria are micron level. So, and there's some small blood cells which are there. The white blood cells are big. Platelets are about 5 to 7 micron. So there is a spread in size between different cells in the blood as well. The advantages of microfluidics is low cost, less reagents. Particularly comes important if you start working with antibodies. Not sure how many of you here are the expensive molecular biologists and pay a fortune for a very, very little antibody. Antibodies are expensive. You don't want to go through grams of it. You don't even want to go through milligrams. If you can do your test with a very small volume, you can save significantly on your bill of antibodies if you can only use a tenth of the amount. So if we look at two different ways that we can organize particle sorting. Very, very similar to mixing. We've got active methods and we've got passive methods. You may start getting aha moments. The things that we call mixing, a lot of that mixing is also sorted by creating certain forces. If the forces are applied to the liquid, the forces are also applied to the particles in the liquid. And some particles will experience a higher force than others, and therefore they'll experience more acceleration. The examples we'll be going through is electrophoresis. We apply not DC potential like we did in electrophoresis, but we apply an AC potential in an asymmetric electric field. Magnetophoresis is when we use a magnet, and we've already seen a lot of magnetic beads coming by, for example, to absorb the DNA. Magnetic beads are really part of the lecture, we'll be talking about passive techniques where we use either the design of the microchannel, we put big post-staphylos in place, and then we look at some particles bump further to the side than others. Again, allows us to do lateral displacement tests. We can look at the normal forces like the inertial lift force. If you've got liquids in a channel, we do have That's always good because pi doesn't change. Has been 3.14 for a couple of hundred years. No plans to change in a hurry. R is the radius, which will differ for different cell types. It depends on the electric permittivity of the particle, and or the permittivity here of the suspending medium, the Reynolds number, so how far it will flow, a weird factor that has got the permittivity of the particle and of the medium in there. I already told you that circulating tumor cells are less compressible than normal cells. Their electrical permittivity is different as well, as is it between different cell types. So the differences in electric permittivity mean that different cell types respond differently in dielectrophoresis. They experience a different dielectrophoretic force, which means that they will focus somewhere differently between these electrodes if we apply this asymmetric fields. So the permittivity controls the high frequency behavior, the conductivity of the media is the low frequency behavior. So depending if we've got positive electrophoresis, when we want to go with particles want to concentrate close to the high density, other particles will want to preferentially go to the lower density fields. So we get different particles go to different places, which is always good because that means that allows us to sort things. So here we've got a dielectrophoresis system where we want to sort out some particles from others. A lot of the slides in today's lectures will be sorting one kind of particle from another. That's what you do with particle separation. So we've got the sample flow coming in here. We've got the sample flow that's coming in, which contains two types of particles. Some of them experience a force going down, a dielectrophoretic force in the asymmetric field. Some of them don't. So some of them will find their way into the acceptor channel here with the buffer flow. Some of them won't. They leave the chip for different outlets, and that becomes the source of our separation. So by doing dielectrophoresis here, we can push some particles into the acceptor flow and not others. We spoke about multidimensional separations before that we get higher resolution. We can also do multidimensional dielectrophoresis, and that's where we first use a field here that's affecting all the particles in our medium to get them all sorted and lined up close to this wall. They all want to be in the high density fields. So both our green and our red marbles cells are all collecting at the left-hand side of the microchannel. We then change to a new electrode here. You can see that we've got a little gap here between the two different electrodes going to the second dimension. First dimension, second dimension. Different potential difference, different AC potential difference applies. Now a little bit more tuned towards one particle or another. So you can see here that the green particles here really want to move towards the other electrodes. The red particles, not as much. Because the green particles feel a much more stronger dielectrophoretic force than the red ones, they get pulled across the middle line. And once pulled across the middle line, they end up in the acceptor channel here. The other particles don't experience enough force, kind of slowly moving away, but very slowly. And in the time it takes to go from the start of the second dimension to the end of it, they haven't made it to the middle of the channel yet, which means that they leave the fluidic system down through the other outlets. So we started with a chaotic mixture. We first use a kind of a broom. We use a dielectric field that swipes up all the particles and gets them nice and close to the wall. And then we come up with kind of a leaf blower where some of the particles get a very big push and they migrate quickly toward the other electrodes. The other particles don't experience the same force, and therefore, by positioning our outlets, we can get them separated into two different fractions. Dielectrophoresis using an AC asymmetric field so that we've got different nodes where, depending on the size and the permittivity, dielectric permittivity of the particles, they will concentrate, focus in one zone or another. The other one that we've already seen coming by is magnetophoresis. And that is the use of magnetic beads for labeling cells and pulling them towards a magnet. So we can use a magnet, we can use a ferrofluid. But if we've got a magnet being put in place, our particles will, if they're paramagnetic, they will preferentially be pulled towards one outlet, whereas other particles don't experience that force. There's no active force pulling this green particle, so we may have now and then have a lost green particle still taking this exit, because there's only an active force pulling the magnetic particles. The other ones don't have an active driving force. If you would like to separate away here the green particles as well, you then need to have a shear flow shielding your magnets away, so that you actively have to pull your particles into the shear flow and taking the left turn. At that point, if there's no active force to pull your green particles into the shear flow, they won't be ending up in your outlet. So here we go. We've got a blood sample, some magnetic beads with certain specific antibodies against the expressing antigens of probably a tumor, circulating tumor cells. So circulating tumor cells have a number of characteristic markers. Magnetic beads specifically stick to these circulating tumor cells. All the blood goes happily towards the outlet for the blood components. But as we've got a magnetic field applied here, the ones that have got a magnetic bead stuck to them all of a sudden feel a force, they're being pulled into the other lines, and our circulating tumor cells end up here in a separate channel. They are the ones that got stuck to a magnet and therefore got pulled by the field into the other lane on the highway. We then have a sensing electrode here that measures the impedance, and it says, yes, I can feel the permittivity of the liquid. Ooh, impedance changes, there must be something bumping over my head. And if the electrodes here record that signal, that's the point where selective collection mechanisms can be activated. So here we've got the ferromagnetic wire that is magnetized by the magnetic field to provide very nice flow path and accelerate migration of these magnetically labeled circulating tumor cells down into the small channel for detection and further processing. If we look how that happens real life, see the further processing, so we'll have a little bit of a look through the microscope, where we indeed can see as soon as we've got a fluorescent labeled particles, it zooms past in our bottom microchannel. It then ends up on a very, very long tube. That's why some level of chip systems are a little bit lost in the laboratory. And then we end up with a fraction collector. If the impedance sensor measures a cell coming by, it knows there's a cell coming, and it will deposit a single cell in every vial in cell culture media, which then allows for the culturing of the circulating tumor cells for further processing, diagnostics, or potentially even drug screening. Because once you know what tumor you're dealing with, you can in the laboratory decide which drug is the best to create the cancer, to treat the cancer that you're dealing with. So fraction collector, which movement will be activated by the sensing of the impedance sensor of the circulating tumor cells that are moving past. So magnetophoresis, magnetic field, dielectrophoresis, alternating asymmetric electric field. Acoustophoresis means that we start working with sound. Sound waves are normally the things you hear because I'm displacing sound waves. Sound waves come through our little pots in our ears when we're listening to music. And sound waves can have a lot of dimensions. They can be here a one-dimensional standing wave. They can be two-dimensional. And all these waves have certain nodes where the energy focuses, and therefore we can focus particles. Rather than showing you a whole range of equations, I decided that we'll download a movie to just see what particles do in an acoustic field, and then we'll look at some microfluidic uses of this. So get back your ears. nice to put a better resolution here, but let's hope that the particle focusing is visible. So we've got a plate in here, and it's got a normal speaker underneath. So there's nothing fancy, sciencey going on. It's just a plate with a speaker that change the frequency at which the sound is coming out. So kitchen salt. Different tones will be played. 345 hertz. You can see by the vibration of the plates, the particles coalesce. They get all together in these nodes where we do the particle focusing. Change the frequency, position, the location of these nodes changes, and therefore all the particles go to the new nodes. And a bit of softness bouncing away. Higher frequency means we get more and more waves coming through. We get increasingly complex patterns. Our focusing nodes change, and our particles are collecting at different locations. So you can see that the location of the particles changes with the frequency. So you can start to imagine that if we apply different frequencies to microchannels, we can also change the locations where particles focus into our microfluidic channels. Right now we've got a symmetric sound field being applied. If we go for an asymmetric field, we may get differential focusing at one place and not at another.
This picture can be repeated. You get the same frequency and
Yeah.
same picture.
The nodes are set by the sound waves. So this is completely repeatable. So all the nodes, if you repeat this experiment, these are the nodes at these frequencies. And if you come back tomorrow, you apply the frequencies again, the nodes will form at exactly the same predictable location.
Is it a special plate or something?
No, just a normal a speaker. So I think they put it somewhere in the description, just a cheap loudspeaker that you get with a portable radio. I've seen people just trying this as a demo in the lab where they just dismantle a cheap speaker they got with their computer, get it to make noise. Every sound has got a different frequency, and you indeed get these patterns being formed. It is the very quick vibration of the surface that causes that there's high energy and low energy nodes. So the complexity of the patterns that form if you go to the higher frequencies really becomes impressive. So if you'd be tuning down voltages and the frequencies again, you'd get back to the original patterns. Yeah. So yeah, if you drop frequency again, then the number of those nodes will decrease. You get the old ones back. So sound is powerful. Sound can move particles. Sound does the same thing in microchannels. So sound moves particles in microchannels as well. And that's why we can use acoustic fields. We can put little surface acoustic waves over the surfaces to play around with these forces and use them for particle manipulation. So if we've got a standing acoustic wave, our particles, depending on their properties, they may move to the node that sits here, and they'll line up in the middle. So particles in suspension, when an acoustic standing wave is imposed, they will feel force, and depending on the acoustic properties of the particle, in comparison with the surrounding medium, they may or may not focus in the high energy nodes. Some physics underpinning it, again, like the other one. If you're keen on trying to do some acoustic focusing, go through the physics. There's a lot of reviews, particularly in Sweden. The Laurel group has worked on this for a very long time, developed a lot of theory, very hard and complex, and also some really accessible papers. So this is the physics underpinning where you can start predicting, depending on the size of the particle, density of the particle, which one will be focusing where. I'll show you a couple of examples of what's being done microfluidically with these sound waves. Here we've got two acoustic transducers sitting at two sides of the channel. You can see that the particles line up in the multiple pressure nodes that are generated by these two speakers. If we put them perpendicular to each other, we don't get lines, we actually get different focusing nodes. So at two sides of the channel, we get lines formed in different nodes. If we put the speakers at both ends, then our high and low energy areas are going to be where those two fields coming from two directions, they meet one another. So as you can see here, we get all the fluorescent particles to be distributed in the grid. If we apply 4 different speakers, and we use some of the mathematics here on the slide before to start programming which one plays what frequency, you can actually start creating letters here, where you can see here that there's some letters being written with particles going in pre-programmed organizations, because it was known what frequency to apply to get them to focus in the right place. Practically, acoustophoresis can be used for cell separation. On the chip here, we can see an acoustic field that's being applied. Again, we've got 2 different fields. We've got a 2-state separation. In the first one, we use so the first one, you use pre-alignment frequency, where we've got 2 different focusing nodes to give all the cells the same starting point when we go to the separation points. Then we go into a wider channel where all particles line up at this focusing node, then end up in a situation where the blue particles don't experience the force to migrate towards the node based on their properties, whereas the red ones do. If the red ones are blood cells and the blue ones are bacteria, we can separate the bacteria away, collect them, and then this particular chip was used for PCR afterwards. So we first put all the cells in one acoustic field in a certain plane. Then we've got the right starting point. The ones that feel a force will move to the middle from both sides. The other ones can move out around the exit hole and go out in the outlet. So they were the different active particle sorting methods to talk about. There's a whole range of particle focusing methods that are passive as well, which either use the fluidic properties, the Newtonian or non-Newtonian fluid, or channel geometries to go one way or another. Here you can see depending on the channel geometries, there's a number of different focusing points for particles because of the inertial forces and the lift forces imposed by the walls. You can see in a circular channel, there's a range of different nodes that is distributed radially. In a square channel, you get 2 different nodes. If the channel is rectangular, the forces on the wall get the particles actually to move back to the center of the channel. Nothing you need to do, just have a liquid flow going through a square microchannel. So here there's the lift forces from the wall positioning the particles at a certain prearranged position as done in this table here. So we've got a certain flow velocity distribution with a quasi flow going through our channel, which means that we get pressure gradients along this uneven flow. We get lift push away forces from the wall, and we get at the same time shear forces because the velocity here is higher than there. We get a bit of spin. And you can see that the particles, after some distance, they start organizing themselves about a quarter of the channel away from the wall. And if they come out, you can collect them in droplets. Slideshow. I need to get back to this screen. So as you can see, the particles come in nicely focused close to the wall. They then are spaced as well because they can sense one another. And with another, with an oil phase coming in, we can very nicely create droplets that each only contain a cell. which then allows us to either add reagents to do lysis, PCR, add reagents to measure proteins that may be secreted by these cells, or do a whole range of other experiments, viability experiments with them, drug assays. But in this system, we create little containers, independent units that each only contain a cell. Not more, not less, one cell each. So that allows you to do experiments at a much larger scale, much better looking at it, population distributions than it would do when you look at in a large cell culture plot.
How to optimize it means every model is containing one cell.
Yeah. Organize the flow rates and your cell concentration so that they are coming in spaced.
Oil is coming to the top. Oil
Oil, yeah.
is coming to the top.
Oh, top and bottom. So there's an oil flow coming from here and here. The cells sit in water. And they try to get the cell suspension right so that every droplet will have a cell. But you can see here we have a part where there's irregularity. Maybe they got sedimentation in the syringe or something. And that means that we've got a couple of them here that are missing their cell. But the vast majority will have one cell only, and it looks here like they've got optimized conditions that they've got certainly no more than one cell per droplet. But yeah, the flow, the spacing between them, you can see the inertial forces actually seem to adjust the spacing between the particles as well, based on the drag forces they leave behind. So you get a very nice and even train of particles, which makes it very predictable at what flow rate you need to work if you know the volume of these bubbles. So you know what volume you need to push out to form a single bubble. So there's good engineers that do the maths there, and then we need to run that 2.3 microliters in it, and we're good to go. So these devices, these inertial separation devices, have really gained a lot of popularity and found a lot of applications in biotechnology labs because they allow for filter-free separation of cells. We've got a single inlet and we've got a channel that just circles around, and if you remember the chips that I had with me, there was one of these devices in there. These channels are not straight, they're slanted. And that means that we get particular focusing effects going on. We get, because we go in the curve, we've got a gravitational force happening as well. And then we get some funky green circulation forces happening in the corner to keep the particles in place. If we work at a very high flow rate, it's pretty much like being in a fair and everybody gets pushed to the outside. So you can see these devices at a high flow rate, all particles move to the outside. However, if we're at a lower flow rate, we can actually get our conditions so that our big particles are recirculated to the middle, where there's less shear, whereas our small particles, the force of equilibrium sits all the way to the outside. A bit counterintuitive, because I always would have thought the bigger ones go outside, but the Dietz force causes some recirculatory effects to get them distributed as indicated here. So that allows, for example, the Cooper's Beer Brewery. We just talked about women don't drink beer, you don't drink a lot of beer here. I like my beer, Australians love their beer. Beer is made by yeast. Yeast is good, yeast makes the beer taste nice, yeast makes the alcohol. Bacteria are not good, bacteria mean that the beer gets smelly and ugly. So during beer brewing, you'd like to keep the yeast from the bacteria. Still, you're doing the brewing as a natural process where actually there's a lot of food for bacteria as well. Cooper's is one of the bit larger microbreweries in South Australia. They had a problem with reoccurring bacterial infections. So they started adopting these devices for separating the bacteria out of their beer brew. They've got stacks of them of 20 or 30 in a row. Don't need to add any other filters. Don't need to add any cleaning. The yeast comes out in one fraction and goes back into the fermenter. The bacteria come out in another fraction and are discarded, which means that they've got much less problems with their beer going off because they can remove their bacteria before they become a significant problem. Centrifugal devices also have been routinely applied to blood product separations. So there's a couple of blood cells, white blood cells that are used for therapeutic purposes. I think they're the T4 helper cells. These are isolated as well using these kind of devices. Because it's very mild, there's no shear, significant shear stresses. A lot of cells don't like filtering because they don't like being squashed to a filter in a really high flow rate environment. Then they rupture and they die. Here the cells are just bouncing around. They don't experience very big forces, which means that they stay generally happy. They've got a very good survival rate. So cells that are used therapeutically are typically better off being dealt with these milder microfluidic approaches than trying with a lot of force to squeeze them to even give up for exchange.
So this is, we are basically upscaling it for the beer, clean beer.
Yeah. So not upscaling, multiplying. Yeah? Because you need to be at a small microfluidic scale to have the phenomena work.
They're making the beer pass through it for the separation?
Yeah.
Small.
But they've got 20 in parallel. So they're all small scale units, like the one that I brought along. But then they just have whole stacks of them. Because you can't make the channel bigger, because then the forces don't work anymore. So the channel needs to stay small. But if you still want to get the beer, all the beer through, you just need lots of them piled up. So parallel processing. Very different way of thinking. But if you have 1 milliliter a minute going through a device, if you've got 25 devices, you've still got 25 milliliters per minute going through. So you don't necessarily need to increase the size of your channel to increase your throughput.
I was just thinking it is upscaling. It's not upscaling the multiplying.
Yeah. I think they call it outscaling. There is something.
Upscaling bigger pipes and everything.
Well, yeah, they can't do bigger pipes.
You're using
So it's multiple plates.
Okay.
So you just get a stack bar. It's like supercomputers. You can't get faster computers, but you can put a lot of computers in a server room. And then you get higher computational power. So I think that's outscaling. There's upscaling and outscaling. I think
upscaling is like from small scale you are making to bigger scale.
Yeah.
Industrial companies.
But yeah, I lost them the word now, but there is a term for doing that by going parallel rather than increasing the real size. But yeah, this is one of the cool things that is a couple of years old now, but has found a significant amount of applications because it's a very mild way of filtering. Another thing that they've done with some blood products to keep them alive is use this for media exchange. So if the cells create any kind of waste products, you can put them through one of these devices. All the cells here under the mild conditions sit in the inner corner. So you can separate out the waste products on the outside, put new media in, and the cells have been cleaned like a happy little baby. So you can wash the cells using these kind of devices as well, with a lot less stress to the cells than when you're getting media out of their cell culture glass and fresh media in, because then there's always things splashing. There's always a few of them that don't survive. So, mild way of playing with the cells. Inertial microfluidics is a field where people have gotten really creative with different channel geometries. So in square ones, we've got certain square focusing nodes. We can put little expansion channels in place where big cells get lost in the expansion channel and can't get out anymore, where small cells kind of just skim past the edges. So if you want to remove a limited amount of large cells from bacteria, for example, they will park themselves in the little side channels here, and you collect only the small channels. You can offset them by making all kinds of shapes. On particle focusing, square corners have a very different effect to round corners, so we get focusing at different nodes, and therefore we can collect from different reservoirs. Spiral channel we just already looked at. Expansion contraction channels we just looked at as well. It's similar to those. And we can use hybrids as well that use multiple particle focusing phenomena in a single device. So you do a pre-screen and then you do a more detailed separation. Onto the viscoelastics, where we start working with non-Newtonian fluids. And what happens under the right conditions if the Reynolds number is greater than 0, and the Wiesenberg number, which is the elastic force over the inertial force. If that's also greater than 1, then you get the particles focusing in the center of the channel. For those of you not quite sure, viscoelastic fluids are drool. So the reason that saliva, there was the young father. You've got these pictures at home, don't you? Just next time, don't think it's drool, just think it's a non-Newtonian fluid coming out. Nice particle focusing effects going on, makes life a lot more hygienic. But in addition to saliva, blood is a viscoelastic fluid as well. DNA solutions are like a lot of polymer solutions behaving non-Newtonian. So viscoelastic fluids can be used for the continuous extraction of plasma from whole blood. Here we've got a channel with some little channels coming out to the sides, so some little defects. When we put a viscoelastic fluid in, then our particles will be focusing all the way to the wall, because for some reason they get afraid of those triangles sticking out. The physics is half understood, not quite yet, but it is really phenomenally to watch that whenever the particle solutions go past, you start as a mess, and every time that there's one of the obstacles coming out, you can see the particles being pushed to the side to then allow for the collection of the red blood cells through this bottom outlet, whereas these two other outlets will end up with plasma. So here there's the different fluids that get collected from the different outlets, where we get the particle outlet gets the red blood cells, so the fluid is red, and we can see plasma-like transparency coming out of the other channels. This one, maybe still a few red blood cells in there, but certainly very well cleaned up and purified. Again, under mild conditions, no big stresses are applied, no filters are being used. We can separate microalgae from bacteria. Again, if you use your microalgae to grow food or to grow energy, you don't want bacteria contamination. Viscoelastic forces, once they're So we've got the algae that are significantly larger and different in size from our bacteria. We inject a mixture in a viscoelastic media, which may mean maybe some BDO or hydroxyapatite cellulose. And then we can see that the bacteria all stay in the central channel, whereas the viscoelastic forces push the algae to the focusing nodes that are close to the wall. If we position our outlets appropriately, we can collect our bacteria in one fraction, our algae in the other two fractions. So if we look face on onto the channel, all our bacteria focus in the middle because of their size. The algae, due to their size, focus at the end. I haven't shown you any equations. A lot of the physics here is still a little bit of a guesswork. So if people see the focusing, they can kind of explain how it works. If you want to do it, what particular things are going to focus, there's quite a lot of things that you got wrong. And one of the reasons we believe that is that all the models are based on perfect spheres, and none of these are perfect spheres. Particularly bacteria, they tend to be rods. They experience very different forces than a lot of fluid that has all the second outlets can actually predict. Sepsis diagnosis. We spoke about sepsis before, where a lot of the traditional culture-based sepsis diagnosis methods take too long, and the patient is already dead by the time the bacteria has been identified. So faster ways of separating the sepsis-causing bacteria is good for early diagnostics. At the same time, you could also see this as some kind of dialysis-like approach, where you can clean the blood from patients with sepsis, remove the bacteria, and reintroduce the clean blood right into them. So here we've got the blood cell and bacteria mixture coming in. PEO is the viscoelastic polymer being introduced. We can see that in the viscoelastic forces that the big cells experience, they draw them into the center. So they get really pulled into the center like a vacuum cleaner, whereas the small bacteria don't have a focusing node there, and they don't experience any forces even if they get into contact with the viscoelastic fluid. Even more so at the boundary, the bacteria experience a repulsive force. So we keep all the blood cells in the viscoelastic fluid here, and we can separate away our bacteria for further testing because we've got that strong push force towards the center for the large particles where our elastic and our lift forces are all balanced out. Here we've got the device in real, where we've got an inlet where we get the different particle streams coming in, where our blood sits, the outlet where we don't see the big particles, except for in the center where we can see that the large cells that were being introduced here at the inlet have all been drawn into the viscoelastic flow. In the middle, we can see here that different particles focus in different positions, which allows us to select certain populations. This graph here gives you a little bit of an idea of the efficiency of the separation, where we've got 2 micron and 5 micron particles. So we're not really talking about a huge difference in size here. 3 micron difference. You can see that the 2 micron particles were very selectively collected at one outlet, whereas the other outlet was highly selective with other larger particles. Very minute difference in size between those particles, 2 or 5 micrometers. Still, we can separate them based on the differences in viscoelastic forces. Again, other approach, you can see the blood cells going straight ahead, smaller cells move to the sides, we can separate our plasma from our blood with very little hemolysis and good yields. Yeah, so this is the recovery of the bacteria in the other outlet, and as you can see, as well in the PVS solution as in the blood, we get most of our bacteria sitting in the blood or in one outlet, and we only have a relatively small amount of bacteria ending up in our other outlet. So it's a very effective way of purifying, separating different cell populations from one another, particularly because we've got this resolution between a couple of microns, which would be incredibly hard to achieve with a normal microfilter. Try to find a filter that allows through 2 micron particles, but not 5. Then there's a range of other passive separation methods. We can do something similar to physical filtration, where we add a kind of a weir structure, where the larger particles simply can't get through. And if instead of having an orthogonal flow, have the flow moving in that direction, we actually have reasonably free transport of liquid in a stress-free environment for the cells. Pillars are being used for difference in bouncing of particles around, which is also called deterministic lateral displacement. I think it's called Penko. As a kid, you may have played with a board where you put a marble in on top, and the marble bounces around and goes left or right at the end. Here, that's been made predictable based on the bounceability, difference in bouncing between large particles and small particles. Large particles will more so deviate around than smaller particles, which means that if you allow them to go through a flow chamber that's got a lot of these different pillars being mounted on the ground, you will be able to separate your larger particles here and your smaller particles more here, because the smaller particles simply, they see less fast, there's less incidence that they've got a collision, so therefore they get deviated less than the bigger particles. Hydrodynamic effects we already talked about when we had the obstacles and the big particles get stuck, whereas the smaller particles can just continue down into the channel. And we can also combine different forces at the same time. So here we've got the Dean flow of going around the corner, and at the same time we can impose on our sample so it's focused in a flow like that. We can then do some focusing as well by just sandwiching that flow vertically so that we can get a sheaf of our inlet. So we first get it all concentrated and then we push it up and down. We can combine dielectrophoresis with some other obstacle channels, combine dielectrophoresis with inertial forces. And here combine the DLD device with some inertial focusing, and then at the end use the magnetic force to give the last little push to get an even higher purity of the collective fraction. So active versus passive separation methods. Which one do you want to do when? Depends on what you want to do. How clean do you want to be? How complex do you want your device to be? How complex do you want your instrumentation to be? So active methods. The advantage is that you've got very precise control. You've got control of the force that you apply to the particles, and therefore you've got control of where they're going. Disadvantage is throughput may be low, and it may require extra infrastructure around your device to operate it. Passive microfluidic methods, simple, can be made high throughput if you stack them together. Disadvantage, slanted channels are not really great to manufacture other than that 3D printing, so that may be a bit of a challenge. And there's not a lot of flexibility. Under certain flow conditions, things separate or not. We don't have a nice toolbox to kind of play around and tune the separation to optimize it for application. Viscoelastic methods are simple and low cost, got good focusing performance, particularly if you go smaller. Disadvantages, the lack of theoretical backgrounds. There's a lot of things in viscoelastic flows that is still poorly understood. So if you've got a passion for, I think physical chemistry deals most of these kind of properties, chemical physics, physical chemistry, there's a lot of work to be done there. And the polymer, if you finally end up with your polymer, with your targets in your viscoelastic solution, you may have to do some tricks to change your conditions to actually get it to bounce out of your viscoelastic comfort zone, back into an aqueous solution again for further processing, because typically cells don't like to have a polymer matrix around for too much longer. The other disadvantage that based on a recent very smart master student that did a project with me is there is an upper limit to viscoelastic focusing, and she found it. Still works at 200 micron channels, falls absolutely to bits depending somewhere at 400 micron channel. 25 micron particle in 400 micron channel, life is still good. 45 micron particle, life is not good anymore. 95 micron particle in 400 micron channel, the inertial forces have overtaken the magnitude of the viscoelastic forces, and you no longer can do viscoelastic focusing. So next time we're talking about this, we probably have a paper on that, we can prove it. It works really good when downscaling though. So nanoparticle separations, there's an increasing number of publications coming out where people have separated submicron particles using viscoelastic microfluidics, because you can combine very high resolution that gets you very narrow size distribution collections of the nanoparticles. So up is not the way to go for viscoelastic. Down has got great potential, particularly because a lot of the other technologies that we've got available for us for particle focusing are not really good dealing, not really having great resolutions, particularly not for particles that are smaller than a micron. And here are some review articles from Dan, a part of the notes that I read through were created by my postdoc Dan, who's done a lot of the viscoelastic focusing. That's done. So there's a couple of really good reviews out there that describe the phenomena. Really interesting field to start looking at, particularly if you've got an interest in physical chemistry phenomena, because the non-Newtonian behavior is actually biosolutions. They still have reasonably low viscosity. You don't think it will behave any difference, but the difference is quite significant, and the consequences are big for our bodies as well, because all the blood flowing in our body is viscoelastic fluid. So the behavior of our platelets and our blood cells going through the capillaries in our bodies, that is all viscoelastic focusing microchannels. They're not microfabricated, but the capillaries in our body are still microchannels. So that was my last official lecture on viscoelastic focusing. Anyone that likes playing around with marbles in the chip? Any questions? So let's have a look at the time. 5 to 4. Yeah, I thought that after the power outage. I was going to do a little bit with the very last lecture, a little bit of a tutorial, going through some papers to see what to look like in a microfluidic. If you read a microfluidic article, how you could best start digesting it. So I'll just open the first few slides for the sake of completeness. Explain the concept, and then we may talk about that during the exam tomorrow in a little bit more detail. So the title of the lecture was Reverse Engineering a Microfluidic Solution. And reverse engineering is, once you know what the answer is, to actually start thinking, how the people developing that ended up with the answer. So you already got a perfectly good eye. But if you start looking what the dimensional data are, have a 3D model, you can start thinking, is this actually the ideal orientation, geometry to have this thing? Maybe yes, because ions have been around for a very long time, and having the whole thing on the bottom of an ion is a good thing. But maybe for iron certain planets, maybe you want to have the side spot as well. Or maybe with people getting larger, hands getting larger, maybe the ions being sold at the moment actually all very small handle. And maybe it's time to increase the handle size. So by going retrospectively through the design process, figure out why all the different parts of an object are there, understanding all the reasons behind it, and thinking, was that smart? Would I have done that? Is it done because it's cheaper? Is it still fine with all the technology that's available, or do we have other solutions? At a certain point, ions only have one temperature. Then people went through a reverse engineering cycle, and they thought, some fabrics melt, other fabrics actually need a really hot iron. Let's put a little pile on there so that we can iron at low temperature and can iron at high temperature. This is the process that engineers do when they want to remake a certain product. It's still good to think what's actually been going on here. And with looking at a microfluidic paper, that's a nice way to go about it as well. Just ask a couple of simple questions. What was done? Was it effective? What are the issues that are still remaining? What are the issues that were not addressed by this paper? First question, and it can be anything in microfluidics, as we've seen, our journals range from microelectronics and mechanical systems, sensors and actuators, analytical chemistry, neuroscience, small material science. There's microfluidic elements popping up everywhere in the literature. So actually, when you find in your literature search a journal that sounds, or an article that sounds interesting, the journal name is probably a first suggestion what kind of the scope of the area of innovation of the paper will be. If it was the Journal of Clinical Research to Hepatic Failure, it's unlikely there will be a lot of technology in there, but you'll have lots of clinical samples. If it will be the advanced materials, the focus will probably be on material science and not on the clinical applications. So, is the paper about an essay? Is it about a new functional model that has been developed? Is it about a new technology? One of the papers I had in mind, if we would have had a bit more time, is tear apart my 3D printing paper from 2014. A new technology. Is it good? How did they make it? Is it easy? Is it hard? How good were the things that they could do with it? So that's then criticizing a technology. Is that a way of making things I'd like to adopt? Or don't I like three-dimensional stuff? Technology can be manufacturing. It can also be about manipulating something. Viscoelastic focusing, up to the point down at my lab, I'd never heard about it. All of a sudden, I could see a whole range of nice and cool things she'd done with viscoelastic forces. So I developed an interest. I thought, maybe that's a nice thing to add to my toolbox. Let's do some more reading. Let's see if I can get my head around this bit of physics. It can also be a full system. It can be about the technology, mechatronic components, the way that it's controlled, or the overall application for an environmental or clinical application. So you can have a paper about a complete system sampling answer out, or a miniaturized total analysis system. You probably will find a lot less detail about every separate functional component in a manuscript describing a full system than in one that's talking about only one module at a time. By the end of the day, most papers in analytical chemistry and these technology journals are 5 to 7, maybe 9 pages. There's only so much writing you can do. If it's about a whole system, it's going to be more diverse. What is the problem the paper addresses? Who knows where you can find the problem the paper addresses? Anyone written a research article? Where, if you're writing a research article, where is the crux of the paper? Where do you write it? This paper is cool. In the abstract. First the intro in the abstract. Any other conclusions? There's one more stuff. Results and discussions in there as well. The end of the introduction. Go to a paper, that little jewel, the end paragraph of the introduction. That contains all the beauty, because the paragraph above that states all the problems in the world that this new solution addresses. If you want to get a really short grasp of what the paper is about, read those last 2 paragraphs. If you want to write a really good paper, make sure those last 2 paragraphs of the introduction are good, because they summarize what this paper is about. This paragraph above, this is the problem the whole world is dealing with, and this is the great solution we've got to offer. Very important thing to look at with a microfluidic paper, because if for your project you're looking for a new way to lyse cells before your protein extraction, and the section in that paper then talks about amplification and faster thermocycling, you've got the wrong paper in front of you. It's not suitable for your research project. So whereas the general blurb in the abstract may still sound suitable because they got efficient lysis and good amplification. And you think efficient lysis, that's what I want. If this paper is then raving on how fast they were in thermocycling, if you're after information for lysing, it's probably not the paper for you. The detail with the microfluidic systems, because there's so much technology, it's always good to do a little bit of a think on what does the device actually look like? How does it work? I do a lot of scribbling on a notepad, drawing the chip, drawing some arrows where forces go. How are the fluids being manipulated? Is it gravity driven? Is it electroosmotic? Is there a syringe pump sitting somewhere? Is it peristaltic? Does it matter how the flow is driven? In chromatography, probably yes. You probably don't want to have a peristaltic pump running your HPLC system. Is there a problem if you've got a peristaltic pump running an immunoassay? Probably not. So understand why the fluid is driven the way it is, and also do a little bit of thinking, if I would change the pump, would it change the performance? Sometimes the answer will be yes, sometimes the answer will be no. How was the chip made? How big are the channels? Was that important? How could I do anything with all this information? If it was glass, was there a reason if it's glass? Or was it just because they have glass manufacturing on their fingertips? It's probably mentioned somewhere in the paper. What kind of extra infrastructure was required to do this research? Did I just need a chip? Or did they also need a confocal microscope? Because then your supervisor must have pretty deep pockets. So I've had never access to a confocal microscope. I'm not sure if you've got one here. But they're pretty hard to get by. So if you can only do something useful with this device, if you've got a confocal microscope or synchrotron, you may want to think again. With all these answers, it's then good to start scribble down, what are the alternatives? Are they equal? Are they better? Are they worse? Does it matter or not? If they're working in the chip with a 2 by 5 micron channel, and you can only make 500 micron channels, if you have the intention of repeating that work, you may want to understand if having that very small channel was critical to the results or not. If they use soft chip lines that you want to copy or some kind of mixer, maybe not. If they use the nano channels to stretch DNA, probably not going to work in a very big channel. I always like to ask myself, would I have done that? Partially to boost my own ego. I like being smart. I like, yeah, I could have done that. I also like the feeling, oh, that was silly, I would have done that better. Sometimes like, that was smart, but that's the thought I really want to have. Because if you read enough of other people's smart ideas, sometimes they may bubble up in the back of your brain as well. So just finding out what was the thing that the researcher here was thinking to get this paper out. What were the issues that they overcame? Could I do this? Could I do this differently? Could I do this better? So they are typically the questions I ask myself. If we wouldn't have had a power outage, we would have criticized 2 or 3 articles using those questions. But I think we've got a little delegation here that wants to take me to the next meeting. The papers for talking about tomorrow are still on this laptop. Still haven't given them to Mr. Yet. So I think we'll distribute them now before we leave. Tomorrow, I think it's the easiest that I first do the online people, have a little bit of a quick chance to ask them very similar questions. So the last lecture today was designed to prime all of you for what we're going to do tomorrow. With the number of people we have, there's probably going to be 7-minute time slots, 2 minutes for walking in and out. So it will be a very quick, informal conversation. No need for really detailed knowledge, but have you grasped the big picture? Do you know why microfluidic system was being used? What it was used for? What was the innovation in this paper? If you can understand 1 or 2 microfluidic papers, I believe you've done an excellent job going through a lot of very broad covering theory over the past 2 weeks with me. And thank you very much for your attention. Any questions? I'll have a list with your names.
And these are signed by several people who are Thank you very much.
Do you have to use the card to get those papers together? So I've got that here on the hard drive.
Can you mail?
I can log in, but then I have to log out the person to log in.
Exam, all exam.
Come on, sorry, I'll get someone else to do that. I'll be very mean tomorrow. Don't sleep tonight.